So we're doing 2.6. I was gonna say it's one of my favorites, but I always think it's one of my favorites because I just like it all. But I think you guys have already started this. You should have started last year. Remember, everything that we're doing from Algebra 2 from now on is preparing you for that beast called calculus. So, no thank you. Who said that? 1, 2, 3. I tap out. So, we're going to revisit the rational equations and the way they behave. And then we'll take a look at some of those graphs as well. So, we're going to be talking about domains. We should already have some idea about these things because we did the rational expressions piece, remember? And the only time we have to be careful with our domain is when there's a denominator, correct? Because what cannot be true about the denominator? It cannot be equal to 0 because once we have 0 down there, we break the math. There's just way too many solutions for us to decide, so we just say no solution because we can't decide on one. Arrow notation, so fancy. We'll talk about vertical asymptotes, horizontal asymptotes, maybe oblique asymptotes. We'll do some transformations, and that's just H and K stuff, right? What does H do to your whole function?
Left and right.
Yeah, it just moves left to right, and K. That's it. It's not fancy. We'll do some graphing. Oh, there we go. We'll get to those slant asymptotes if we have time. If we don't have time, because I know it's a shorter day, then we'll just pick it up tomorrow. But we'll go as far as we can. Definitely 3 types of asymptotes to look out for: vertical, horizontal, and those slant asymptotes, aka oblique asymptotes. And then if we have time for some applied problems, then we'll do that as well. Any questions on these objectives? Anyone that sounds confusing? No. All right, cool beans. We'll get to what they mean later on. And of course, a rational function, we know that it's simply it's the quotient of 2 functions, correct? So we have in this case p of x over q of x, blah. Now domain. All we're really looking for domain is what values of x does this function take on. So that's all you're really looking for. What are all the x values of this function? Sometimes you can't have some because the denominator, we don't want it to be 0. Therefore, we find when that happens and we say everything except for these positions, or maybe it doesn't exist from here to here kind of thing, okay? So it should just be all of the x values. All of the x values. Mm-hmm. Alrighty, cool beans. So let's start off with talking about this one, okay? So, like I said, we've done this already. We're just revisiting. We're looking at a little bit more. The question is, what is the domain of this thing? Well, obviously, we see that there's a problem here, correct? Okay, where's my problem?
On top.
Bottom. The bottom cannot be,
Yeah.
it can't be 0, correct? So, that means that x cannot equal how much? 5. But then the question comes up, is this an asymptote? For starters, 5 cannot be in my domain, no matter what. Okay? But then we have to decide between whether it's a asymptote or a removable discontinuity. Okay? So in this case, what is it? Any ideas? Yeah, so if we take a look at the top, that is a difference of squares, correct? So I'm going to have x plus 5 over x minus 5. My denominator happens to be x minus 5. And it looks like these make a 1. They make a 1. Which means I've removed that situation, haven't I? I no longer have a problem denominator. So in this case, it's called a removable discontinuity. So I might get this curve that's smooth and continuous, but there'd just be a hole wherever 5 is at. Does that make sense? Questions on that? Preguntas? Pregúntame. Are you getting Wi-Fi on that thing?
What's the answer?
Okay, so the domain, let's see here. Let's go with x as an element of all real numbers except x cannot equal 5. They're going to do the so what is this called? Do you guys remember? Set builder. So if we're going to do it in interval notation, then we're going to go negative infinita all the way to 5. And then we're going to go, yeah, because we're not equal to that, right? And from 5 to positive infinita.
Yeah, why is it not union?
Why is it what? Oh, yeah. Should be or. I mean, yeah, or. Union. La Casa no union. How else can I write it? Oh. How else can I write it?
X cannot equal 5. That's the way to write it.
In a paragraph.
Yeah.
In a paragraph. Or a graph. I don't know if I want to do a graph.
I think I'm gonna write a paragraph in math.
Yes? Just wait till you get to those upper maths when we're starting to write everything. You guys good? All right, here you go. You try. You try. Oh, you weren't done? I'm sorry. Well, there was a lot of talking. It's because you don't have a garbage disposal.
That's the only reason. Okay, I'm good now.
All right. Cool beans. Anybody else delete this slide? Blue, you're good? Okay. You try this one now. X over x squared minus 25. Find the domain, please.
Oh. How do you want it written?
However you prefer.
Her not right.
What's that middle bit?
Búsquenle el dominio y el rango. No? So. So let me ask you this question. What kind of denominator? Not me. What kind of denominator not here? 0. So here's what we're going to do. We're going to ask algebra. Hey, algebra. When does x squared minus 25 equal 0? Because once we know that, then we're going to say, you can't be those numbers. Does that make sense? So, when we do that, that this function is equal to 0 when x is 5 or negative 5. So, hey, it can be any number except for what? Well, you could. Which one are you using? Set builder or set builder is just kind of like the top one I did. So I can say, hey, you know what? For the name, I'm gonna say x is an element of all reals except x cannot be plus or minus 5. So that's it. I love to right. Now, if you want to do this in these intervals, think about this. Here is everything, right? Except, over here, on this side, there's going to be a hole, or a lower and asymptote, and negative 5. So these spots don't exist here. So what I'm looking at is, okay, I'm coming from negative 10, and I'm going to go all the way to negative 5. And then I'm going to go from negative 5 all the way to positive 5. And then I'm going to go from positive 5 all the way to infinity. And that's all we're really doing. Are the asymptotes in this? Oh yeah, they are. Because they're not removed. Oh yeah, so these are asymptotes. You are correct. Nope, you're right. There it is.
No, hey, the answer's up there. Yeah, that's what I did.
Pretty much all controversy has to be false. You can't.
They've changed that again. Yeah, like honestly, I don't know. That's what I was saying.
Alright, cool. Here we go. So, what cannot be the denominator here? What can this not equal? It cannot equal 0. Okay? It cannot equal 0. So we ask algebra, hey algebra, when does that equal 0? Right? Because that's going to lead us to finding those values. So once we do that, we find that x is equal to plus or minus 5. So whenever the value of x is a positive or a negative 5, that would break this, wouldn't it? Okay, so now I know what I cannot be. So that means, that means that x can be an element of all real numbers except x cannot equal plus or minus 5. And there's your step builder notation. Questions on that?
What's the thing next to the x?
This is a I always draw like an E, but it's that represents element. So, for example, let's say I did have a set here. Oops, I skipped 4, didn't I? Anyways, let's do that. Is 4 an element of this set? No. And that's what we use. So, the symbol is element. Let me see if I can Google it for you. You can see the actual one. Can you see it? Oh, it's so tiny. Oh, good idea. There it is. Oh, this is not an element. This is element.
That's just an E.
So it's not an E. It's because some people would argue it's a C. Actually,
It's like this.
actually,
When you're about to tell us that.
no. Here's what the symbol really looks like. You guys remember? The symbol for union? It kind of looks like that, and the symbol for and looks like that. Element is the same sign sideways with an E, like a line through it. So it's that same symbol just spun, and it has that line through it. And then of course, if you do this, it's not an element. I know, it's kind of trippy. But you see that a lot when we start doing probability and sets and combinatorics. I just said too much too fast, didn't I? Okay, so the study of counting is called combinatorics. And you'll use those symbols a lot. That's all I'm going to say. Cool beans? All right. What's up? So remember I asked you, is 4 an element? You would say X is not an element of, let's call this I, of set I. So there will be your notation. That make sense? No? Okay, so, but what's the name of this set? It's I. And I asked the question, hey, you know what? Is 4 an element? You would say, oh, hold on. You don't say that. You're right. You would say 4 is not an element of I. Yeah. Sorry. Yeah, when I looked at it and I read it like, oh, that doesn't make sense. All right, go again, go, go.
No water.
We look at right in terms of I.
Oh, that's what I thought.
Ha! No,
Yeah.
not in this case because.
And this is
Oh,
two different things.
it would be, but not really. You're not going to get imaginaries, guys. Just stop for a second. I know. So, and I have a video I want to show you guys because since you asked me like about the applications, I've been more interested in knowing more. Like I was satisfied with knowing that it gets used in electronics and stuff, but then I was like, that's not really like I'm not going to go there. What other things they have? So I'm listening to this guy from MIT, and he says, yeah, you know what? It does come up a lot, like in what do you say, quantum mechanics and all these other things. But you can't really. I know. That's all. Like I don't know how to do that. But people ask, and I'll show you guys a snippet of the video later on. But even though they get used, they're kind of like go-throughs. Okay. You guys remember like parabolas, right? When we do parabolas, and if they're above the line, do they have real intercepts? No. And the problem is sometimes not everything is a parabola. Sometimes things can be cubic functions, but you're trying to find some values and you're trying to solve for some unknown. And sometimes you bump into that scenario where I kind of have to work with these complex numbers. And then once I've done that, and I think you guys have noticed, right, at the end, like when we're working backwards, we had complex solutions, but what ended up happening when we went back to the model? Those complex values or those imaginaries just went away, didn't they? So what he was saying is, even though you're working with those imaginaries at some point, eventually they're just kind of like a pass by. You kind of use them, move on, so you can get to your real solutions and the real numbers that you're looking for. Because those other things are kind of conceptual, but sometimes there's just no way to get from point A to point B without having to manipulate some type of complex number. Which was like, oh, okay. Because I mean, it makes sense, right? Measurements are real. degrees are real, all these different things are real, but at some point, you might have to cross some imaginary values that you're just gonna have to deal with them, move them away, so you can get to your real numbers that you're looking for. Now, for this problem, don't sit there and try to find all the I values. If I put a positive number in there, is it gonna become 0? Will the denominator ever be 0? No. If I put a negative number in there, will that function ever become 0? What if I put 0 in there? Will the denominator become 0? There's nothing I can do to break it. See that? So we can sit there and we can force ourselves to go through those complex motions, but why in the end? Because they're not useful to us, right? So no matter what I put in here, I'm not breaking this. There's no way I can. If I put positives, negatives in there, they're all going to become positive. That just gets bigger. There's no way that I can break this. Okay? Now, if it's a minus, that's a different story, right? Because maybe I can take away enough where it becomes a negative value, and then I don't want that. But in this case, there's nothing I can do. I mean, even if I put 5 in there, I'm going to end up with 50. So for this case, what's the domain? All real numbers. You're always going to have some value here. Okay.
I don't like that.
This is some of that calculus coming through now. Okay, they're going to call this arrow notation. Now, everyone understands that we are usually graphing stuff, right?
Yeah.
And I might be looking for, let's say maybe this x value. And in this case, we're looking at x, at some value, x, as we approach from the positive side. So as I come in from the positive side, what number am I getting close to? Does that make sense? So I'm approaching some value from the positive side. On the other hand, it's this, right? What value am I approaching from the negative side? Now, in this case, it might seem like irrelevant, right? Because aren't they both approaching the same thing? Does that make sense? So that's okay. But sometimes I might have functions where they might be doing this, and this part might be doing this. Right? And maybe the x value that I'm looking for happens to be that. Hey, what am I approaching from? No, that's not what I want, because that would be wrong. That would still be okay. Let's see here. Let's do maybe like this or something. Okay? All right. So you notice how I'm approaching two different things? One from the positive side, one from the negative side. Two different things? That happens sometimes. Do you guys remember the expression from Mean Girls, the limit does not exist?
Yes.
That's the definition right there. When your function is approaching two very different values from either side, then the limit does not exist. In the last example, they were approaching the same thing, correct? Then the limit does exist. Maybe I should have said anything.
So like in that, the limit doesn't exist?
Yeah, because are they approaching the same thing?
No.
No, they're not.
But in the first one.
But in the first one, they're both approaching the same thing, right?
Yeah.
So the limit does exist. And that point, whatever it is, would be the limit. It would be the limit. Oh, I got a question for you. Let's say that point was actually one of those removable discontinuities. Okay, let's say that the removable discontinuity was at 5, because we had a removable one at 5, didn't we? So now we're approaching from both sides this removable discontinuity. Does the limit exist?
Yes.
Yeah, it does. Oh, we did this, didn't we already?
No.
I feel like we did.
Lily's just not smart.
Okay, maybe I'm having flashbacks from last year. So yeah, even though we're still approaching that. Now, does the value exist?
No.
No. Does the limit exist?
Yes.
Does the value exist?
No.
Simple enough?
That's weird.
I mean,
That's pretty cool, huh?
What's that? It's like if
same thing.
Okay. Questions on the other two symbols? Approaching infinity without stopping. Approaching negative infinity without stopping. Any questions? I think I felt like I said a lot of different things.
you did.
No, I get it. Lily had a
We're all
definition.
struggling with our information.
You're not okay with that?
No, I'm okay with it.
Okay, this is what I really care about the most.
Oh, the simple part?
So, for example, take a look here.
Oh, brother.
Oh no, we're defining a vertical asymptote. So, let's see here. The line x equals a is a vertical asymptote of the graph of the function f if f increases or decreases without bound as it approaches a. Okay, so yeah. So if you notice that you don't know this is an asymptote, but you're noticing that this is kind of getting closer and closer to some specific value, then that might just be an asymptote. Make sense? What is that? You guys okay? No? Okay, so same idea. This is just in reverse. We're approaching from the positive side, but we're going down towards negative infinity. Here we're approaching from the negative side, and we're headed down towards negative infinity. Let's see here. Locating vertical asymptotes. This you definitely want. Okay? If p of x over q of x is a rational function in which p of x and q of x have no common factors, and a is a zero of q of x, the denominator then, x equals a, is a vertical asymptote. So in other words, in simple words, you guys ready for the English translation? I feel like I have to give you a little visual, okay?
I was ready for the English.
So, let's say we had this scenario. Okay, so this is what it's saying. These are completely factored, correct? Do they have common factors in the top and in the bottom? No. That means that these two are vertical asymptotes. Okay, it's all it's saying is what I've been telling you the whole time. There's no removable discontinuity, correct? So that means that these are vertical asymptotes. If I could remove them, then would it be a vertical asymptote?
No, it'd be a hole.
It would be a hole. That's what this is saying. What's up?
How do you know it's removable? Because it's on the top too.
Yeah, so if I had x minus 5, what happens with anything over itself? Don't say it cancels out. It's 1, good. So now it's a 1, and now I've removed this x minus 5, kind of removed it from the scenario, right? So no longer a vertical asymptote, now it would just be a hole. Do I still have an asymptote here though? Yes, and it would happen at negative 5. Make sense? Okay, cool. Questions on finding vertical asymptotes? We've already, I'm canceled?
You heard this, Mr. Munoz.
Say that again?
You're canceled, sir.
Okay, can I just sit down there?
Yes.
You can figure it out on your own. Okay, so finding vertical asymptotes. So in this case, again, does this have vertical asymptotes?
Trick question.
Right, trick question, because can the denominator be factored? No, it cannot. So I'm not going to be able to find those pieces there, okay? So notice that there are no vertical asymptotes here, are there? Okay? Cool beans. Horizontal asymptotes. Horizontal asymptotes. These are going to be a little bit more... you're going to have to do a little bit more math on this, Mills, to find these. But notice how this kind of gets closer and closer to some value. We have a horizontal asymptote. Same idea here. Same idea over on this side. But do notice that this one does cross at some point. Because I think that for the longest we've been told you can never cross an asymptote, right? But you can with the horizontal sometimes. So just an FYI. Yeah. Usually it's just horizontals that we cross. Okay?
Yeah, you thought you could give. Nah, that wasn't a trick question.
You guys okay with this? Just showing you some horizontal asymptotes, what they look like. And yes, in some cases, we can cross it. Okay?
What happens if you cross it?
Nothing, it just goes on forever.
Let's just
On some ends, it will follow that asymptote, but sometimes it will cross it and it just can't carry on. See, like in this, on the left side, it crosses, it just goes on forever, right? But on the right side, it gets closer and closer and closer and closer to that asymptote. Okay? It's trippy, huh? Okay? I don't know if I want to scare you guys with that yet. Let's see here. Maybe I want to chunk it. I think I want to chunk it down. Yep. Close your eyes for like 5 seconds, please. This is my blind. Okay, cool. Here we go. Thank you. 4 horizontal. That is bad. For horizontal asymptotes, you have to be careful with these, okay? So, there's going to be 3 rules that you need to know. And I'm going to chunk it down because if I throw them at you, you probably go crazy with those. So, we're going to let f be a rational function given by, so here's my function, correct? Now, hold on, slow down. All you're really looking at, when we've done this, is the definition of a polynomial on top, and it's over the same definition of a polynomial, correct? Remember, the highest x down to the lowest x. Same thing for this guy though, but we can't use a because now we have a different function. So this is from the highest m down to the lowest m. So all you're looking at is the definition of 2 functions that go all the way from the highest to the lowest. Simple enough?
Yeah.
Okay? So I know it looks crazy. It's really not. How? Because we have to have standard definitions so that anybody can read them. Okay? We can't make like our own rules here, and then I can expect you to go and take a standardized test and be like, passing it if I don't use the same language. It's got to be standardized, okay? We're good? Okay, so the degree of the numerator is n, and the degree of the denominator is m. You understand that? You guys see that from the example up there? Here's our first rule. If n is less than m, then the horizontal asymptote will be the line y equals 0. Simple enough? So, if the top one is smaller than the bottom degree, so this is a 2, this is a 3, this is an x, this is a square, then your horizontal asymptote will be the x-axis, aka y equals 0. Anybody need a visual of that?
Yeah, I would
So,
very much like it.
let's see if this will write on here, okay? So let's say, well, it's not going to write, so let me do this.
What's the second rule?
So if I had y equals, sorry, not y equals, yeah, we'll stick with f of x. So let's say maybe I had x squared plus 2x minus 5 over x to the third plus 2x minus squared minus 3x plus 2. I don't know, I made those up. What's the degree of the top? 2. What's the degree of the bottom?
3.
The top is less than the bottom, correct? Then that means that when I graph this thing, the x-axis is going to be the asymptote. It's going to be a horizontal asymptote. That's all it's saying. And I think that you have seen that before in the example y equals 1 over x. What's the degree of the top? 0. What's the degree of the bottom? 1. Do you guys remember what this looks like? This is my asymptote, right? And it kind of does this bit. Because this is an asymptote now. Because of that rule. Okay? So when the top one is smaller than the bottom one, then the line y equals x will be your asymptote. Okay? Questions on that? Next rule. If they are the same, degree, then you're going to take a ratio of the leading coefficients. And that will be your horizontal asymptote. So if they are the same, meaning, where to go? If I have y equals 2x squared over x squared, then that means that I'm going to have a horizontal asymptote over at 2. And y2? 2 over 1. The leading coefficient here is that, and that's my ratio. Excuse me, Mr. Box. Questions? Go ahead.
Was there more than one horizontal?
Can't have that. Because there's only those rules. It's going to be where it's less than, where it's equal to, or it's greater than. Okay? Questions on this? Last rule. It's when the numerator is bigger than the denominator. In this case, there is no horizontal asymptotes. But there's a but. There's a but. So, do you guys have this rule? So, if the numerator degree is higher than the denominator one, you will have no horizontal asymptotes. But you might have oblique asymptotes or those slant asymptotes. Okay? So don't think they dropped the hook at that point. And that's it. See how it wasn't bad?
I did this on the review and I was completely confused.
And now you're not. Now you're just less confused.
I did the degree part.
The degree part?
Yeah, like
Cool.
the biggest degree.
Mhm. You guys good?
Exactly.
You guys are kicking it. Oh.
Mr. Munoz, we know all this function, all the books.
How do you get the
I have no idea.
Waterfalls. Go ahead.
How do you get the graph where that you did on the other page?
How do I get the graph that I did on the other page? This one?
Like no, the one where it was like
Oh, 1 over x?
here's and the curve down there.
1 over x?
Yeah.
The reciprocal function?
Yeah.
That's our mother function for well look, here, take a look. Is this x removable? No, so that means that I'm gonna get an asymptote at x equals 0, correct? Isn't that an asymptote for this function? Yeah. Now let's take a look at the other rules. This degree is smaller than this one, isn't it? So I take the ratio. Or sorry, no. Because this one is smaller, that means that the line y equals 0 will be an asymptote, and there's my other asymptote. See that? So we'll start breaking it down a little bit further. What's up?
How do you do the one where it's like that, but then in the middle it has one of these?
That's a cube function.
Okay.
We'll talk about those later on, okay? We're gonna get to those. Just we're gonna do baby steps, okay? Check it out. Look at this beautiful problem here. So, in this case, we're looking for just all the asymptotes, okay? Now, for starters, are there horizontal asymptotes? Yeah, there are, right? No, there's not. At 3? What makes this 0?
Oh wait, no.
Nothing makes it 0, correct? So, am I going to have horizontal asymptotes? No. Well, I have vertical asymptotes. Well, here, look. 3x squared equals -1, divide by 3. Once I do that, I've got imaginary values. So I'm not going to get real asymptotes here. Okay? So no horizontals. Will I have, I will have no verticals. Will I have horizontal asymptotes? Where at? Ah, that's what you're saying. You were right. I was wrong. I was using the wrong word. So there's our function right there. Okay. Let's take a look at same one. Why the same one? Why same one? What?
Not the same one.
Why do you have the same one?
They weren't the same. They were.
No, the
Oh! Good eye. Good eye. Good eye. That one is though, right? That one is the same? This one? Waterfalls. Go ahead, Therese. How we did this? Well, for starters, we said vertical axis. We'll pick it up tomorrow.